Okay, before talking about springs, looking back at velocity time graphs, the last thing was that we know that speed multiplied by time gives you distance. And once again, we can just interchange speed and velocity. So, if you want to find the total distance of the journey, all you have to do is find the the product of this and this. So you just times them two together, and that's known as finding area under the graph. Yeah. So whenever you have a velocity time graph, and they want you to find the distance traveled, if it's for the whole journey, you need to find the entire area of the whole graph. Now, the way you can do this is, you can split it into two triangles and a rectangle, depending on the shape. So this is a trapezium. Obviously, if you don't know the formula for area for trapezium, then you can just you split it up and find it individually. So I'll show you two methods. First method is you find the area of this triangle first. So it'll be like what? Half base times height. So it'll be half times base times height. We're doing for the triangle 1. The base is what, 50, and the height is 2. So it'll be like half times 50 times 2. And then for the second part, this part is just rectangle, so length times width. So the gap there is between 150, which is 50, and the height is 2. So it'll be 50 times 2 gives you 100. This one gave you 50. And then for the third part, you want this triangle again. So this will be the gap between them, which is 50 as well, times 2. So you just do half times 50 times 2. You get 50. And all you do is you add all these areas together to be 50, 50, and 100, which gives you 200 meters. That's the total distance. So that's how you find it. They might have only asked you what's the distance traveled for the first 50 seconds, in which case you only had to do this part, which represented the first 50 seconds. What they could have said between 50 and 100, and you just do that. So it depends, really. Anyhow, moving on to Hooke's law. With Hooke's law, what we need to understand is this formula here. You need to memorize it. The force applied on the spring is equal to the spring constant, which is a constant value, times the extension. So, explaining this, because no one seems to get it because the name is a bit elusive. Spring constant can also be called spring stiffness. So, the stiffer a spring is, the harder it is to pull and squeeze together, correct? So, the greater your spring constant or spring stiffness is, the greater the force required to actually extend it. Which does make sense, because if you make spring constant or spring stiffness the subject, you end up with this. So what we're trying to say is, if this goes up, that means, basically, yeah. So if you look here, if this goes up, that means the force required to extend the spring also goes up, pretty much. You don't need that. My bad. So you have an unextended spring with no weight on it, no force on it. It looks like this. When you apply a 5 Newton force, it extends by a certain amount. The extension is the difference between your original length and your new length, which is this gap here. Yeah. So if we look at this question very quickly, underline all the numbers we have. We know that extension is equal to 20 centimeters, but we always deal with extension in meters. So changing it to meters, we divide it by 100, you get 0.2 meters. So centimeters to meters, always divide by 100. What else do we have? We got our force F is 10 newtons, and we want the spring constant, which is K. So all we do is we use Hooke's law. F equals KE. So rearranging for K, K is equal to F over E. And you have 10 divided by 0.2, which gives you 50. The units for it is, what's the units for force? Newtons divided by, what's the units for extension? Meters. Bam, easy. It's 50 Newton meters. Next thing about springs is they store elastic energy within them. So elastic energy is stored within anything which you can compress together, squeeze, or you can stretch it. Yeah. So the formula for this, and it's given in the formula sheet, so don't worry, is half multiplied by spring constant or spring stiffness multiplied by the extension squared. So what we need to understand is, once again, the greater the spring stiffness or constant, the greater the force required to extend or compress it. That's pretty much what you need to know. Let's do one example maybe very quickly, right? So we know the formula for elastic energy, once again, is half times spring constant times extension squared. They might tell you in the question, spring is extended by 10 centimeters if energy stored is 200 joules. What is spring constant, right? And this might be like a 3 marker because you have to rearrange, so it's a bit harder. So let's just write everything we have. We got the extension, which is 10 centimeters, but we do not like centimeters, so change it to meters. We got the energy stored, so you can use capital E for that, 200 joules. And we're trying to look for K. So looking at this formula here, this is all equal to elastic energy. Yeah. So to find your spring constant, let's rearrange this formula. So what does it look like is your spring constant is equal to your elastic energy, which let's just write E of capitals for elastic energy, divided by everything else that you want to get rid of. Because when you want one thing, you have to get rid of the things on the same side with it, so you divide by them. So it'll be half times E squared at the bottom. So elastic energy is how much? 200 divided by, the half always remains half. Just write 0.5, looks better. And your extension is 0.1 meters, but don't forget to square it.